Right. So now let us today take up Laplace transforms, which I started mentioning last time, but then now today we will look at what they are and what the salient properties are. So, and I pointed out that if you are given a function f of t in the range t greater than or equal to 0, then for instance f of t could be a response function like the ones we looked at in linear response theory, then an integral transform of this function is extremely useful in solving say differential equations involving such functions or many other equivalent problems, and the transform is defined as the Laplace transform of f of t is defined as I call it f tilde of s. This by definition is 0 to infinity dt e to the minus st f of t. Okay. Now the moment I write this, I need to tell you immediately in what range of s, this parameter s or variable s, does this integral converge. Now normally we would look at functions f of t which could of course go to 0 as t tends to infinity or go to some constant or maybe even diverge, but it is clear that unless this diverges extremely badly, and we will say exactly how badly it should be, as long as the real part of s is greater than a certain value, such an integral is expected to converge, okay, because it will kill whatever divergence this might have. Okay. Now to start with, let us write real s greater than some number c, some positive number c say, could even be negative if you are lucky, but in general as long as real s is bigger than a certain threshold value, you expect this integral to converge. Okay. Now of course there are immediately lots of functions which can't satisfy this condition at all. For instance, if this f of t increase like e to the power t squared as t becomes large, then no matter how large real s is, how large positive, you are not going to be able to get the integral to converge. Such functions do not have Laplace transforms, but a huge class of functions obviously does have Laplace transforms, and we define it in this fashion, and it is immediately obvious by inspection that this thing here in the S plane to the right of some number c, it is an analytic function, as you can see by inspection. In particular, if S is real on the real axis, then there is a nice well defined integral. If you give it an imaginary part, all this does is to give you an oscillatory part, and this integral continues to converge. So by now we have enough experience to say that it is an analytic function to the right of some number. Okay. Now of course the question immediately arises, how do I continue it analytically to the left of this line, and we will see explicitly various examples of how to do this. Now immediately simple functions f of t, we could write down the Laplace transform at once. So let us start by saying f of t equal to, here is a function which t to the alpha e to the minus at, so where alpha and a are some constants. Then this thing says f tilde of s equal to, I put in t to the alpha here, and then this becomes s plus a times t. I change variables to s plus a t, and it is some gamma function as you can see, and the answer is gamma of alpha plus 1 over s plus a to the power alpha plus 1. Now for what values of alpha and a would you expect this integral to converge to start with? Well, remember that what is involved is f tilde of s is 0 to infinity dt e to the minus s plus a times t to the power alpha here. This factor could give you trouble at the lower end if alpha is sufficiently negative, right. So you would like real alpha to be greater than minus 1, otherwise that integral is not going to exist. Okay. Similarly on this end s plus a, it is clear that as long as the real part of s plus a is greater than 0, you got convergence at infinity, right. So real part of s greater than S plus A greater than 0. Okay. So you specify some A and some alpha, in general some complex numbers, and as long as I keep S in that range and alpha in this range, I am alright, the integral exists. But once I have done the integral, once I have finished doing it and here is the answer, you can analytically continue this in both alpha and A to whatever complex value you please. Now this immediately tells you, as you can see, there was a condition here said real S plus A must be greater than 0, so you expect some problem when real S is equal to minus A, and indeed you can see that at S equal to minus A there is a singularity of this function here, and in general for complex alpha it is a branch point of some kind. So this explicit form tells you what the singularity structure is, but you keep these parameters in this range to start with, do the integral, and then there is an explicit analytic continuation. Okay. Now many special cases come out. For instance, if you set A equal to 0, this will imply that the Laplace transform of this function t to the power alpha is gamma of alpha plus 1 over S to the alpha plus 1. And of course if alpha is some integer n, positive integer n, then it is n factorial over S to the n plus 1. A very important lesson comes out here, and that is the large t behavior of this quantity here is governed by the small s behavior of the transform. As you can see, if t tends to infinity and alpha has got a positive real part, this thing diverges, and that divergence appears in the Laplace transform in the form of what happens near S equal to 0. So there is a well developed theory which tells you how to find the asymptotic t tending to infinity behavior of f of t based on the s tending to 0 behavior of the Laplace transform, and similarly how to tell the t tending to 0 behavior based on the s tending to infinity. Both ways. These are called Abelian and Tauberian theorems. We will come across some examples of it a little later, but right now I want you to see right from this formula itself that the large t behavior intuitively is governed by the small s behavior here. This is going to be a useful piece of information. If you put alpha equal to 0, for instance, implies Laplace transform of e to the power minus at is 1 over S plus A. In fact, as you can see, if you got any function f of t and you multiply it by an exponential like e to the minus at, all you are doing is to shift the Laplace transform variable by a. So it follows immediately that the Laplace transform of any f of t e to the minus at is equal to f tilde of s plus a, where f tilde of s is the Laplace transform of f of t. So all it does is to shift the s variable by a. That too is a very useful thing to remember. What about the convolution of two functions? Well, we need to know what happens to the product of two functions, what happens to the Laplace transform, and it is a simple matter to show that a quantity like 0 to t dt prime, say f of t prime and g of t minus t prime, this is called a convolution of f with g. The Laplace transform of this combination, such a combination, is equal to f tilde of s g tilde of s. So convolution gets translated into multiplication as far as the Laplace transform is concerned, a very useful thing, and you can now have a convolution of many functions one after the other, and then the Laplace transforms would just get multiplied in this fashion. So again, a very useful theorem. Notice the t, the limit t here, 0 to t, that is the way the convolution theorem works for Laplace transforms. I urge you to establish this, it is very straightforward. All you have to do is to write down the transforms of each of these and then do a little bit of algebra and you get this. What about the Laplace transform of the derivative f dash of t, where this stands for the derivative with respect to t? Once again, put this in the definition and integrate once by parts, and if you integrate by parts, then it immediately follows this is equal to s f tilde of s minus a boundary term which is f of 0. That is going to come when you integrate by parts. The infinity part goes away because of the e to the minus st, but the 0 contributes and you have this. Well, you can proceed one step further and take f double prime of t. This is equal to s squared f tilde of s minus s f of 0 minus f prime of 0. These are not transforms, these are the values of the original function at 0 and its derivative at t equal to 0 and so on. So, the Laplace transform of the nth derivative is s to the power n times the original Laplace transform, and then a polynomial which involves s and polynomial in s which involves all the initial data, all the derivatives, the function's value and its n minus 1 derivatives at t equal to 0. Okay. So, this tells you that the operation of differentiation is being converted to the operation of multiplication by s here, and that is very useful when you want to solve differential equations. Okay. So, that is where it comes from. You can convert different ordinary differential equations in s can be converted by this trick of Laplace transforms into multiplication by s. So, you get algebraic functions, and then the question is how do you invert the transform. Okay. Now, the inversion of the transform involves a little more work. Inverse Laplace transform. This is called the Mellin formula. It says if f tilde of s equal to the Laplace transform of f of t, then f of t is 1 over 2 pi I, a contour integral over f tilde of s, but remember you have to be in the region of analyticity of f tilde of s, otherwise the integral does not make sense, and that is some right half plane. So, this is ds e to the plus st f tilde or f of t, sorry, f tilde of s, where the contour runs in the following way. If this is the region of analyticity in the S plane of f tilde of s, and I said it is some right half plane to the right of some point, then the contour is a line parallel to the imaginary axis running from c minus I infinity to c plus I infinity in this fashion. And since the contour does not cross any singularities or anything like that, and the function is analytic, you can deform this contour and you can move it up and down on this side. What you can't do is to bring it to the left here, because you are not guaranteed that f tilde of s is analytic there. And in general, of course, f tilde of s will not be analytic. We saw even for the function t to the alpha, there was an, or e to the, for this function the Laplace transform of t to the alpha was equal to gamma of alpha plus 1 over s to the alpha plus 1. So, we saw that in this case the region of analyticity is realized strictly positive, and at s equal to 0 there is a singularity. So, in that case it is in fact a branch point, there is a branch point here and there is a cut running to the left here. You certainly can't bring the contour down to this side, okay, not in its original form anyway. So, this thing here is called the Mellin formula. Okay. And the question is, how are we going to use it? How are we going to use this to evaluate the inverse transform? Now, let us look at a simple example. Let us look at this case where we had, let us look at the simplest case. The Laplace transform of e to the minus at was 1 over s plus a. Okay. So, that function has a pole at s equal to minus a somewhere. That pole is to some point, we do not care where this a is, but we have a pole at this point here. Okay. How would you now evaluate this line integral with a pole here? Well, you try to use the residue theorem, right. the way to do this is, of course in this case we can move the contour to the left up to this point. You can move it all the way to the left provided you pick up the contribution from this pole here. But another way of doing this would be to say, alright, let me attach an infinite semicircle of this kind, and if this function vanishes sufficiently rapidly at infinity on this side, then of course you are in good shape. It means that you can evaluate this integral, this contribution becoming 0. Now notice that this circle runs over real S negative. That is what we have done out here on the left hand side, and there is a plus sign here as opposed to the original Laplace transform, which was e to the minus st was the kernel. Now the kernel is e to the plus st. So this contribution is guaranteed to vanish provided this function is good enough because of this factor here. And it is immediately clear that if f tilde of s is any rational function of s, ratio of two polynomials, it has got a whole lot of poles at various points in some left half plane, then this trick is going to work, because all you have to do is to close this contour, and now you can shrink it and pick up the residues from all the poles. So it is immediately obvious that as soon as you have a rational function of s as f tilde of s, the inversion is very trivial. All you have to do is to close this, and that is the end of it. Now when you have more complicated functions, more complicated singularities, then it is not so trivial. For instance, in this simple case, this function here itself, in order to produce this function back for you from this contour integral, I have to put in here 1 over s to the power alpha, alpha plus 1, and then what is it that I can do? Well, the best you can do is there is a branch cut in the s plane of this function. The original contour was like this, and I can fold it over and make it like this. And if I know the discontinuity of this function 1 over s to the alpha plus 1 across this cut, I can convert it, provided the integral exists, into a line integral from there to minus infinity, and then try to do this integral. Okay. So the moment you have branch points, it is a little trickier to find the inverse transform. But if you have just poles, as would be the case of a rational function, then it is very straightforward to do this. So there are lots of examples, and some of them are given to you in the exercises. Okay, so much for the inversion. Let us look at a couple of problems which we are going to be talking about Bessel functions a little bit, because they occur at various places. But before I do that, let me give an example of a second order differential equation which you can solve with Laplace transforms, and this is the famous simple harmonic oscillator problem, the damped oscillator or the series LCR circuit, for which in terms of the charge q in the circuit, so LCR series circuit, the equation looks like L q double dot of t plus R q dot of t plus 1 over C q of t is the applied voltage on the right hand side, and let us say it is a sinusoidal voltage, so some V naught sine omega t say. So that is the second order differential equation governing the charge on the capacitor, instantaneous charge in a series LCR circuit. Okay. Now of course the first thing to do is to divide through this by this L, and then identify the fact that you have R over L equal to the time constant of an LR circuit, and in the absence of damping there is a natural frequency for the tank circuit, LC circuit, which is 1 over square root of LC. So it is convenient to express everything in terms of these two parameters, and then as you know, once you have this, you switch it on, then this circuit, depending on whether it is under damped, over damped or critically damped, will reach a steady state in which the current itself and the charge will also oscillate with the frequency omega, but the forcing frequency omega, but there is a transient, and you can compute what the transient is explicitly. So I leave you to do that as an exercise. All you have to do now is to use Laplace transforms, and then this becomes S squared times something or the other, and this with an S and this with the f tilde itself, collect them together and invert this transform because it is a rational function. And you have 3 cases, you have omega naught greater than, equal to, less than half gamma. They correspond to overdamped, underdamped, critically damped, and overdamped. So this is that and this that, and the equality is the critically damped case. Okay. So you can solve the problem for any one of these cases, and then the others can be read out by analytic continuation. Now what normally happens is that in the underdamped case you have an effective frequency which is omega squared minus gamma squared over 4 with a square root, and in the underdamped case this is a real number down here inside the square root, and therefore you get oscillations which are damped with e to the minus half gamma t or whatever times this frequency, functions at this frequency. That will be the transient part, and then there is a steady state part which will have a frequency omega here. And you are used to doing this by calling them the particular integral and the complementary function. Okay. So what's the purpose of using this complementary function for an inhomogeneous equation? An equation like this, an inhomogeneous equation, the right hand side is non-zero. So you know the general solution is a linear combination of a particular integral and a complementary function. Why do you add this complementary function? It is a solution to the homogeneous equation, right? You add a certain amount of it. Why do you do that at all? Apart from the fact that it's the most general solution, but how much of it do you add? What decides? What decides how much of this complementary function you add to the particular integral? What do you need to make the solution unique? Initial conditions, yeah. So the purpose of adding the complementary function in a suitable admixture is to ensure that the initial conditions are satisfied. That is what decides it for any inhomogeneous equation. So I urge you to do this in the overdamped case, and then in the underdamped case, and then continue analytically to the overdamped case. Typically what will happen is that this quantity here, this square root will become pure imaginary in one case, and then trigonometric functions will go over into hyperbolic functions. Okay. So it is a nice little exercise to try it out explicitly. Okay. Now let us look at some more interesting problems in this very standard problem. I have in mind a problem from probability theory, from the theory of random processes, because that is where we use a lot of this, and it involves what are called Bessel functions. This particular problem I am going to talk about involves Bessel functions. You are all familiar no doubt with the original definition of the simplest Bessel function of all, the Bessel function of the first kind of order n or something like that. Now what does this look like? I like to define it in the following way. First of all, I define it as a function of a complex variable always, and the order is nu, and that could be complex as well, okay. And let us define it. I define it in the following way: summation n equal to 0 to infinity z over 2 to the power nu plus 2n divided by n factorial, and then a gamma of nu plus n plus 1 and minus 1 to the power n. Okay. If you like, that is my definition. You could also define it as a regular solution of Bessel's differential equation, and that is how you probably come across it for the first time, but this is a good definition here. Nu is any complex number you like. In general it is a complex number, but when you specify that it is an integer, for instance if you put nu equal to a positive integer n, then it turns out that j nu, jn and j minus n are not linearly independent of each other, and you have jn as one solution and you have the Neumann function as the other linearly independent solution. But for arbitrary nu, this is one solution here, and j minus nu is also an independent solution. What can you say about the analytic properties of this in Z? What sort of function do you expect it to be? Do you think this series has a finite radius of convergence or an infinite radius of convergence? That is a power series in Z squared sitting up there. The fact that you have Z to the power nu comes out of the integral. So there is definitely a Z to the nu, you can take out Z over 2 to the power nu, and then it is this. This part for arbitrary nu has a branch point at nu equal to 0 and at infinity. So let us leave that out. What can you say about this series? What would be the radius of convergence? Infinite, yeah. There are two factorials. There is a factorial here and there is another gamma function here. So this is certainly, this portion is an entire function. And if nu is an integer, the whole thing is an entire function. The leading behavior as z goes to 0 is proportional to z to the power nu, as you can see here. So that is a nice entire function of z, and that is the Bessel function of the first kind of order nu. Okay. Now what about its Laplace transform? Well, we want this for a function of t, for instance. So let us look at for instance, let us look at j0 of at, where a is some constant. What is this equal to? This is summation n equal to 0 to infinity at over 2 minus 1 to the power n, this to the power 2n divided by n factorial, factor twice because nu is 0, squared out here. We can find its Laplace transform. All you have to do is to remember the Laplace transform of this function. So the Laplace transform of j0 of at, this is equal to summation n equal to 0 to infinity minus 1 to the power n, n factorial, and then a to the 2n over 2 to the power 2n, and the Laplace transform of t to the power 2n, but we just saw what the Laplace transform of t to the power n factorial was, right? So this is a 2n factorial divided by s to the power 2n plus 1. So let us take out one factor of s, and this is 1 over s, and let us write this as a squared over s squared to the power n. And the fact that you got a 2n factorial on top, n factorial downstairs suggests very strongly this is some binomial expansion of some kind. So I urge you to prove that this is equal to 1 over square root of s squared plus a squared. That is a very well known result, and it follows directly from here. Check this out. So unlike the earlier cases, the Laplace transform of a Bessel function is not a rational function. It has got branch points at s is equal to plus or minus ia. It has branch point, inverse square root branch points in these places. Similarly, you could write down the Laplace transform of j nu in general. It has got branch points in s. So it will involve the square root combinations and so on and so forth. Okay. By the way, there is an interesting integral which can be done immediately, and that is if you put a equal to 0, if you put s equal to 0, then you get a 1 over a. So there is a well known integral which says 0 to infinity dt j0 of at equal to 1 over a, positive a. Okay. So you can also use, once you get a Laplace transform, you can put in various values and get various integrals of special functions also, but that is a very well known result. Okay. So now let us turn to the physical problem. I have in mind? So, the process I have in mind is part of a class of processes, random processes called Markov processes. And in the simplest instance which we are going to look at today, this process is a random variable, has only discrete integer values. Okay. In fact, it is called a Poisson process, and the random variable concerned takes on values n equal to 0, 1, 2, etc. So, all the non-negative integers, those are going to be the value. This n changes randomly with time by a prescribed rule, and the sample space is 0, 1, 2, 3, etc. Okay. And the problem we have in mind is that of radioactive decay. So, you have this huge sample of some radioactive substance, and you have a counter, and you start measuring how many decays occur. So, you clock every time there is a decay of a nucleus that occurs, it clicks in your counter. At t equal to 0, you start afresh with a huge sample, and then you let the thing start decaying. As you know, radioactive decay proceeds at random. You can't say which nucleus is going to decay when, it proceeds at random with some average rate. So, on the time axis, this is my t equal to 0, I put a cross every time there is a decay. So, one occurs here, another occurs here, in quick succession you have two of them, and then a gap, and then another one, and so on, and the interval between these decay events is random, completely random. These decays are independent of each other. So, the sample is sufficiently big that different parts of it, different nuclei decay quite independent of each other. There is a certain average rate of decays, and let us call that lambda equal to mean decay rate, in the sense that if you give me a sufficiently small interval of time dt, the probability that one decay occurs in this time interval is lambda dt, and the probability that no decay occurs at all is 1 minus lambda dt. Then the question asked is the following. So, this thing is called a Poisson process, and we are seeking the probability Pn of t that in a time interval t from the time I started the clock, exactly n decays have occurred, n events have occurred. Now, it is clear that this n is an non-decreasing function of t. Okay. In other words, n can only increase as time goes along, and each time it increases by 1. If you drew this n, if you plotted this n as a function of t, you would end up with some kind of as a function of t, a typical n of t. A typical graph of this would be, well, nothing happens for a while, and then there is a decay, and then it is quickly followed by 2 more decays, and then nothing happens for a long time, and then there is a decay, and so on. So, it increases by 1 each time. Okay. The question is, what is Pn of t? Well, we immediately know that Pn of 0 is equal to delta of n comma 0. At t equal to 0, no decays have occurred, so P0 of 0 is unity, and Pn of 0 is 0 for all n greater than 1, no decays have occurred. Now, how are we going to find this Pn of t? We have assumed that these decays are independent of each other, they are completely statistically uncorrelated, and there is a certain mean rate of decay. This is what part of what is called a Markov process. So, we ask, what is Pn of t plus delta t equal to? What could this possibly be? Well, at time t plus delta t, if you want the probability that exactly n decays have occurred, then one possibility is that at time t, n minus 1 decays have occurred, and in the interval dt, one more decay has occurred, right. So, that probability is P n minus 1 of t multiplied by lambda dt, lambda delta t. So, this is the probability that one decay occurs in time interval delta t, this infinitesimal interval, and that is the probability that n minus 1 of them have already occurred at time t. Okay. And the only other possibility is that you have P n of t n have already occurred till time t, and then nothing happens in the time interval between t and t plus delta t, and the probability for that is 1 minus lambda delta t. That is it. These are the only possibilities. They are two independent mutually exclusive possibilities, and therefore you add the probabilities for each of these. And in each case it is a compound probability. You need n minus 1 of them have to have occurred till time t, that is p n minus 1 t, and then multiplied by the probability that 1 occurs in time delta t, and similarly for the other term. Okay. Now move this p n of t to the left, divide by delta t, and you take the limit, and you immediately get dp n dt equal to lambda times p n minus 1 of t minus p n t, which is true for n greater than or equal to 1. Okay. Yeah.
So why couldn't we have 2 decay in time?
Good question. Why couldn't you have 2 decays in time delta t? The answer is, if you have a finite rate, mean rate lambda, then the idea is that it is possible for you to choose a delta t sufficiently small that only 1 decay occurs in it. In other words, this process has what is called a finite transition rate. That is necessary. Yeah. Pardon me? Yeah, the whole point is that the assumption is that you can choose your delta t small enough that there is no simultaneous 2 decays possible. That is an assumption. And it is justified. I mean, we are going to go to the limit in which delta t goes to 0, as a matter of fact. Okay. But this is only true, this equation is only true for n greater than or equal to 1. For n equal to 0, you need a different equation, because what happens now is the rate at which dp0 over dt changes is minus lambda p0 of t, because from 0 you can only go up to 1, you can't go to minus 1 left. So you had no decay at all, and then all that can happen is that there is a decay at some stage. But that equation immediately can be solved, and this implies that p0 of t is e to the minus lambda t times p0 of 0, but that is unity, that is 1 because of this. So we have a set of coupled differential equations. They are very simple equations, they are linear, but they are coupled equations, and we need to solve it. And what do you do in such cases when you have a set of recursion relations of this kind? You define a generating function. So let us define a generating function. I mean, you can solve this set of equations much more trivially, but let us do it by the generating function, because we are going to use it in other cases. F of z comma t is defined as summation n equal to 1 to infinity Pn of t z to the power n. So the idea is I am going to write a differential equations for f, solve this differential equation, and then write out f of zt explicitly and pick out the coefficient of z to the n in its power series about z equal to 0 and call that Pn of t. That is what it is. Now what should I do? Well, I ought to multiply this equation on both sides by z to the power n of this guy, and then sum from n equal to 1 to infinity. Okay. By the way, what is the boundary condition on this function? F of z comma 0, the initial condition. What should be the initial condition? Remember, this starts from 1, 0, because all these probabilities are 0 at t equal to 0, except p naught of t. P naught of t does not appear in this generating function. So this is equal to 0. That is the initial condition. So what does this tell me? Well, the left hand side is delta over delta t f of z comma t, and that is equal to, on the right hand side you have this term lambda times p n minus 1 of t multiplied by z to the power n. So lambda summation n equal to 1 to infinity p n minus 1 of t z to the power n, in this fashion, minus lambda times f. So I am going to simply multiply that by z to the power n and sum from 1 to infinity. And what does this give me? This is equal to lambda times, I will pull out the n equal to 0 term, n equal to 1 term here. This gives me p0, that is e to the minus lambda t, and then there is a z. So this is lambda z, and then the next term is plus lambda summation n equal to 2 to infinity p n minus 1 z to the power n minus lambda f. Okay. So this term, let us call this n minus 1 and multiply by z here, and this guy runs from 2 to infinity, so I will call n minus 1 equal to n prime or something like that. So n prime will run from 1 to infinity, and this is just f once again. So it says delta f over delta t equal to minus lambda plus lambda into 1 minus z f equal to lambda z e to the minus lambda t, right? That's it. We can solve that equation. It is an inhomogeneous equation, first order, standard form, but let us do it using Laplace transforms just for the heck of it. So I am going to call the Laplace transform of this with respect to t, I am going to call it f tilde, and then I get s f tilde of z comma s plus lambda times 1 minus z f tilde of s. So let us put the whole thing together, s plus lambda minus lambda z f tilde of s equal to lambda z over s plus lambda. Because the Laplace transform of e to the minus lambda t is 1 over s plus lambda. Okay. So that gives me something I can invert. It says f tilde of s equal to lambda z over s plus lambda times s plus lambda minus lambda z, and the obvious thing to do is to write this as partial fractions, 1 over s plus lambda. Let's write this as 1 over s plus lambda minus lambda z minus 1 over z, and then if I do that I get 1 over lambda z, so this is 1 over lambda z, right? And this obligingly cancels out and just gives me these two rational functions. So that immediately tells me what f of z comma t is equal to, it is the inverse Laplace transform of this here. So it is equal to e to the power minus lambda t plus lambda t z minus e to the minus lambda t, which is e to the minus lambda t comes out, and then e to the lambda z t minus 1. That's it. Check that the boundary condition is right, because you put t equal to 0, this vanishes as it did. Okay. And all we need for Pn of t is to find the coefficient of z to the n in this, and that is trivial because it is immediately sitting right here. Okay. So what is the final answer? P n of t equal to e to the minus lambda t to the power n factorial. And incidentally it is true for 0 as well, because we already know P naught is e to the minus lambda t. That is the Poisson process. Now you know this is a Poisson distribution with a certain average, and what is the average value? Lambda t, as it should be. What is the average number of decays that occur in time interval t? Lambda t, because lambda is the average rate of decay, right, as it should be. So this here is a Poisson distribution with lambda t as the average. So if you like, we could write n of t equal to lambda t, and all the other properties of the Poisson distribution are well known to you. The variance is equal to the mean, the standard deviation is equal to the square root of the mean, the relative fluctuation goes like 1 over the square root of the mean, and so on. In fact, for the Poisson process, all the cumulants are also equal to the mean, lambda t. Now that is what simple radioactive decay does. This is an example of what is called a birth process, because this random variable n cannot decrease. As t increases, it must either stay where it was or it must go up, it can't go down. So it is just a pure birth process.